In this relative rates problem, we have a situation with a ladder that's a constant 10 feet long. It's just resting right here. Here's my ladder. And it's a constant, it's made out of metal probably and doesn't have any, it doesn't change at all. It's resting against this vertical wall. So here's my wall here. The bottom of the ladder starts to slide away. So here's the distance. X is the distance between the wall and the bottom of the ladder. And as it starts to slide away, X starts to change. So this ladder is kind of sneaking, it's going this way a little bit. So as time passes, X gets larger as it starts sliding away. So that's the bottom of the ladder slides away from the wall, and it says at a rate of 1 foot per second. So the ladder sliding away from the wall at that rate, that's really saying how fast is X increasing as it starts to slide away. So change in X over change in time. That's what dx over dt means. So they're telling us that's sliding away about 1 foot per second. And as it's sliding, the ladder is, of course, a constant, it's just a constant size. It doesn't change at all. So as that's sliding down the wall, the top of the ladder is sliding down the wall. So this is saying, in orange, it's saying, how fast is that happening? So that's another way of saying, what's the rate? How fast, how much is Y changing? Y is the distance between the floor and the top of the ladder. So how fast is that changing in relation to time as the bottom is sliding out? So dy dt is this sentence, and how the speed of the bottom pulling away from the wall is dx dt. So we've been given dx dt, and we're asked to find dy dt. Okay, so we also asked, of course, that rate might change as time passes. So we're also told specifically when. I want to look at it when, at the moment that X is equal to 6 feet. So when this is 6 feet, when this equals 6, what is the rate of change when X equals 6? What is the rate of change of Y with respect to T at that moment that the ladder is 6 feet away from the wall? All right, so these are our steps to solve this problem. So we just did step 1 and kind of did step 2 while we were doing that. A little bit of step 3, but we'll keep going with that. I think with step 3, let's use purple. So let's do step 3 now and assign some notation to all the quantities in the function that are functions of time. So what are we given here? Let's see, we're given that the length of so this is my step 1, my step 2, step 3. They gave us the length of the ladder is, I'm going to erase this since I have it over there on the right there, so I can move this up. L will be the length of the ladder. And that's a constant, and we've been given that as 10. And let's let X be the distance of the bottom of the ladder from the wall. So as it's sliding down, we'll have a dx dt, measuring that speed as that x is getting bigger and bigger. And then we have y. Y is the distance, or the position, the distance between the floor and the top of the ladder. Or in other words, the height of this little triangle that we've made. The x is kind of the base of this triangle that we've made. The ladder is really the hypotenuse, since this does a right angle. So this is really a hypotenuse of this right triangle that we've made. That's pretty much all our variables, except, let's see, we got dx dt, that's actually step 4. So expressing the two rates in terms of derivatives, one rate is given and the other rate is the one we need to find. So they gave us dx dt, that's the rate, the bottom slides away from the wall. And they actually gave that one to us. They gave dx dt is actually equal to 1. That's what they gave us in that blue highlight. The ladder slides away from the wall at a rate of 1 foot per second. So that was given to us. So that's that. And then we're asked to find dy dt. That's the question mark. That's our unknown. That is how fast the top of the ladder slides down the wall. And we want to know what is dy dt at that very moment that x equals 6. So we actually want to define it. I'll do it like this. We want to evaluate it at x equals 6. Okay, so we've defined all our variables and our derivatives, or our rates in terms of derivatives. So now we're going to go to step 5 to write the equation that relates these quantities. So x, y, l, what is the relationship between those? Well, it looks like it's making a right triangle, and we're just talking about the three sides. So 3 sides of a right triangle are related by the Pythagorean theorem. So that gives us step 5. So x squared plus y squared equals L squared, and L squared we know is 10, so that's x squared plus y squared equals 100 squared. So that's our relationship. Now it's time to do step 6. Step 6 says we're going to use the chain rule to differentiate both sides of that equation with respect to time. And that's why we need the chain rule, because time is not in that equation. So these functions, x and y, are really a function of time, because both of them are moving as time passes. So really, x is a function of time, y is a function of time. So when I take the derivative of them, I want to treat that as a function of time. So d of x squared, d dt of x squared plus y squared, and d dt of 100, oh, sorry, that 100 should not be squared, of 100 So the right side is easy because that's just a derivative of a constant, which is 0. And then I need to take the derivative of x squared. So x is a function of t. So I think chain rule. Okay, so I take so my x is kind of my inside function. So I take the derivative of the outside function, which is like my inside function squared. So it's 2x times the derivative of the inside function. And since that's not explicitly expressed, I just call it that for now. And then I also do the same thing with the y. So y is 2y times the derivative of y. Okay. So I got my differentiation I've derived both sides. Now it's time to substitute the given information. So I know they've given us L. I already plugged that one in. We also know dx dt is 1. So that means I can plug in 1 for right here. And they've also given us the x. They want us to evaluate it when x equals 6. So this x is 6. And of course, 2 is a constant, so that comes out in front. And then we have plus another 2. Y, how do we get y? Well, let's see, we can actually use this equation, or this one actually. So when we know x is 6, so we can use that equation and say when x is 6, then I can plug that into my Pythagorean theorem and solve for y. So subtracting 36 from both sides, and then y equals 8. So now I can plug in an 8 for for y. And dy dt is my unknown. And it's the only thing I don't know, and that's the thing I'm going to solve for now. That brings us to step 8. In step 8, we're going to solve for the unknown. The only thing we don't know is the dy dt. So I'm going to simplify this a little bit. So I get 12 plus 16 dy dt equals 0. Solving for dy dt is subtract 12 from both sides. And I get dy dt equals negative 12 over 16, which simplifies to negative 3/4. So that is my dy dt evaluated at x equals 6 is equal to negative 3/4. It's a negative because it's changing by falling down the wall. So that negative shows that downward fall, that direction. And then the 3/4 is the speed. So it's moving at, this is in feet per square for second. So it's moving at 3 feet per 4 seconds. My last step, to state the answer in terms of the context of the original problem. So again, the rate changes throughout this event, but we've picked out exactly what the rate is when the ladder is 6 feet away from the wall. So step 9, to state that final answer, at the moment that the bottom of the ladder is 6 feet from the wall, the top of the ladder is falling at a rate of 3/4 feet per second. We got a negative 3/4, but that is kind of embedded in that word falling. The fact that I already said it's falling gives me that negative. So there's my final answer.